It is a pleasure to see all of you this morning, this afternoon, and for some participants from the West Coast of the US, it would be very late at night. Welcome. We have a very interesting program ahead of us today. And I'm very happy that we can start today with two colleagues who are working in the condensed matter field, because as part of this workshop, we are obviously the organizers are originating from the high energy side of this business, and our intention was to seek out what are the activities and what is the progress that is being made also in other communities. And therefore, I'm very happy that Andre and Hiroshi agreed to present this morning. And we will start with Andre Mishchenko. He is a researcher at RIKEN in Japan, and he will tell us about analytic continuation, a new philosophy as answers to well-posed questions for ill-posed problems. Andre, could you share your screen, please?
Well, I can start.
Yes, please.
So I will tell about analytic continuation. So some new things which we recently developed. And I'm from RIKEN, as I told, and here is a photo of RIKEN in the suburbs of Tokyo. And here is the Tokyo semicircular highway, which is very near to RIKEN. And here is a map of Japan where RIKEN is located, and all speakers are located in this area. And as I told you already, it's 1 hour by car to discuss something, so it's no problem for us to discuss it without going to Trento. And what I'm going to tell now is about analytic continuation. I will give some introduction, and then I describe why it's difficult, why this problem is called to be ill-posed. And then I said that the main goal of us, for many years ago, we started this activity. And our goal was to obtain solutions which are dictated solely by the data and not corrupted by some useful constraints, which in particular is a regularization. And I will describe why we hate the regularization and why it's not so good to use a regularization. Then I explain why stochastic approach is so useful, because it have no apparent regularization. And the second is a new philosophy which follows from our recent job, which we did several years ago. And in this recent job, we understood that is no sense to search for the best solution, because all solutions which satisfy the input data are the best. And we can place a linear combination of this best solution, and every combination which we use is also the best. And then I show you what follows from this. Okay, so what is analytic continuation? Analytic continuation, so I will tell about numeric analytic continuation, although it looks like very funny, but it's numeric analytic continuation. So the thing is, do you see my cursor?
Yes.
Okay, so this is the thing which is known from somewhere. It can be known from experiment, from some many-body calculation by exact technique, and this is the function which is known. This is the function which we need to find, so it's a required answer. And this is the kernel which connects this thing to this thing. So the analytic continuation is knowing this, obtain this, is just to get the thing which is under the integral, and the integral is a kind of it's called the Fredholm integral of the first kind. So actually, in the general form, this equation looks like in the following way. It's known function from somewhere, from experiment or from some theoretical calculation. It's a function we want to know, and this is a kernel. And it's related to many problems. It is related in theoretical physics, it is related to some calculation. For example, this can be some correlation function or green function, which is obtained as a calculation. This is the spectral function, or for example, some kind of correlation function, current correlation function. And this is the kernel which relates this function and this function. And this kernel can be of any form. It can be very complicated, like through current correlation function, and it can be anything. Moreover, this equation is very famous because it is related to many things in real life. So for example, it's a known problem of the image deblurring. This is two-dimensional vector in this case, and this is two-dimensional vector in this case. And we have some original. And we know about the scattering function, which smears it and goes. And then using the deblurring, solving this equation, we can obtain the image with some level of accuracy. Another thing is when you go to the hospital and somebody sent you to magnetoresonance investigation, it's absolutely the same problem. So you have the function which is three-dimensional, which is scattered radiation from your body, and you have some distribution of the density of your body, and you have some kernel which is known, and what is done, why MRI is not immediately available, because you need to solve this equation to get the answer, what is this inside your body. So actually, this equation is known for many things. It's necessary to solve to reach the aircraft stability. It's necessary to when you have the nuclear reactor operation. And actually, this is the reason why I studied this equation 25 years ago. And what is the problem with this equation? In general, the problem is there is no exact solution. First, it's a first statement, which is very important. Why it is ill-defined problem. If you know this function with some noise, it's easy to understand that there is no exact solution which exactly match this equation. So in principle, there is no exact solution at all. So the question comes, what we are going to find? So if there is no solution, what thing we have to find? So when I tell about, in the end, about new philosophy, which we have now. So before, the philosophy of solving this equation was the following. Although we do not have the exact solution, we search for single approximate solution, which is considered to be best by some artificially chosen criterion. So our new philosophy which comes, and which is now our philosophy. So every solution which is dictated by the input data, so here's the input data, is the best, because every solution which satisfies the input data within the accuracy error bars of the input data are the best. Every solution is the best. So we can play with the linear combination of this best solution to get an understanding what is the all possible solution which satisfies the input data. So let's go a little bit to history. So if you look at this equation and go to different places, you find the different answers and different methods to this equation. If you get to the financial department, in financial department, everybody say, okay, I know this equation. It's usually solved by the ridge regression method. If you go to the engineering department, then everybody says, okay, it's Tikhonov regularization, it's known, so don't worry, it's only one and the best method. In physics department, the situation is more rich because once I wrote a review, it more than 30 different methods to solve this equation with different approaches. And actually what I'm going to say about some new method which do not enter into this method. So, okay, Tikhonov regularization is engineering department, and I'm going to tell about one of the next plate is stochastic method and methods of linear combination. Okay, what is bad? So because there is no exact solution, we need to understand how we got this result. So for example, we take the deviation of this some solution, we choose some solution, and consider the deviation from the input data. And this is the Euclidean measure. Okay, so we will try to find the best solution by minimization the Euclidean measure. So actually, if our task is to minimize the Euclidean measure, then from the point of view of the linear algebra, there is an exact answer. So you calculate the left singular vector of this matrix, right singular vector of this matrix, and these are singular values of the left and right singular vectors. And then there is explicit expression for this solution. So you can ask me, what is the problem? If it is possible, if it is enough data here, and if it is possible to find the analytic expression for this solution, why it's problem? The problem is the following. So this expression is good when you have absolutely exact data. And sometimes what is interfere with this data, even the computer accuracy. So if you look at the solution, so here the smooth curve is a real solution. And if you use this formula, and even within the limit of the computer accuracy, not with real error bars, which comes from the experimental calculation, even with computer accuracy, you see such result for this explicit formula. So it means that this explicit formula in this direct form is useless because it leads to the called sawtooth instability. So when the instability of solution is much larger than the solution itself.
Andre,
so there is a way.
Andre, sorry,
Yeah.
there is a question from the audience. Could you briefly say what is the product operation between the UI and the VI? UI, it's direct product. Direct product. Thank you. Yeah, but it's formula from the textbook. So it's you open the fourth chapter of the textbook for linear algebra, and this is a formula for solving such equation. Yep. But the problem is that sawtooth instability is much larger than the solution itself. So first remedy for this thing was found by Tikhonov in 1941. This is the first method in Moscow before World War II. It was found that if you filter out the small singular values, then you can reproduce this solution very well. So was the sense of the Tikhonov regularization. And since that time, the fashion is to use the regularization to solve this equation. So in every scheme of the regularization, one minimize not just the m, which is a deviation measure. So I just return back. So this is a deviation measure. And in principle, this is everything which is dictated to us by the data. So if one uses the regularization, one minimize not just this measure by add some additional functional which corrupts the solution. So there are many many schemes of the regularization. This is cutoff of small eigenstate, which is Tikhonov case. Filters.
No, come on.
Who is this? Let me. Sorry. Please continue. I have muted.
Okay, so there are many kinds of the regularization. And all these methods corrupt results. So what is regularization? So instead of minimizing this Euclidean measure, which is the only measure which is dictated by the input data, one adds some extra functional, and this extra functional just forbids the big derivatives, filter out the small eigenvalues. But in any case, in addition to the measure which is dictated only by the input data, one has a functional which fights the sawtooth instability, but this functional in some way corrupts the input data. So actually, 30 years ago, I was lucky to hear for this guy as my professor for the regularization methods. And he is, one of the most frequent authors of the Tikhonov itself. He was very old, 75 years old, but still his lectures were very bright. And what he said during his lectures that all regularization methods are bad. So our dream was to avoid the regularization. And that was our idea, say 20 years ago. So why we need to avoid this regularization at that time? So my main activity is diagrammatic Monte Carlo. It's just a few minutes, 1 minute to advertise. It's a method of exact summation of Feynman diagrams for green function and correlated function. So maybe 50 years ago, Feynman gifted Feynman expansion from the particle theory to the condensed matter physicist, and condensed matter physicists use this. And finally, there is a group of authors which developed the exact summation of Feynman diagrams and correlation function method. And maybe there are some papers which contain this, but what is good, so we can exactly sum the Feynman diagrams for green functions and correlating function, but all these results which you obtain are imaginary time and Matsubara frequencies. So to get an answer, we need the analytic continuation, and I going back to our task, it's to avoid the regularization, which can be disastrous in case of the, for example, if we study the quasi-particle spectrum. Okay, so what our approach? We just, for example, take some configuration. So this is the spectral function, and this is omega, and we parameterize the configuration by some rectangles which given widths, height, and so forth. So this is continuous parameterization. So it does not contain some predefined mesh or whatever, because it can be also disastrous. And what we do, we take some randomly chosen initial configuration and make the naive minimization without any regularization. As a result of this non-regularized minimization, of course, we have the sawtooth noise instability, because if no regularization, there is sawtooth instability. But we do another things. We take another initial configuration and again get some minimization, and we obtain another answer. This answer also has a sawtooth noise instability because there is no regularization. But then we start to do the tricky thing, not tricky thing, but very simple thing. We start to average these solutions. So for example, this dotted line gives you the spectrum, which is typical for the quasi-particle spectrum. There is a delta function, which contains a quasi-particle. In the left corner, this is a delta function. This is the gap. And this is what is called usually incoherent part of the green function, of the spectral function. So here, if we use some kind of regularization, then instead of delta function, we have some peak, and there is no such good feature for the gap function. So it's impossible with regularization to obtain this spectrum. But every solution which we got is the solution without regularization. And if we start to average these solutions, so here is the average of the four solutions. If we take 28 solution, you see that the sawtooth noise always disappear, but still we have delta function and very sharp gap. And if we go to 500 solution, then we have perfectly disappeared sawtooth noise, and we have still delta function and perfect gap. So actually, what we have that we have many solutions. So since we have many solutions, we can say that we can have the error bars because there is a fluctuation of the solution. And the main thing that no one of this solution contains any kind of regularization. So it means that we do not use the smoothness of solution. We do not exploit any kind of the truncation. So every solution is the best one, which is dictated only by the data. And the sawtooth noise instability is defeated by the way of the averaging of the solution. So this is the state of art we have got many years ago in 2000. And because in 2000, we published it only in the appendix of this paper. So if you want to find it there, you should go to the back of the paper, and there is the last page with appendix. And if you're interested more, there is a tutorial thing on the correlated electrons from models to materials in Jülich. And this was the state of art of the many years ago. So the next question we asked ourselves several years ago was the following. So as a result of our procedure, we obtained many solutions. And for our understanding, all solutions are the best because every solution satisfies the input data within the error bars. So because all the solutions come to satisfy the input data within the error bars, all of them are good. So, and in contrast to the 99% of the methods which solve such kind of equation, we are not going to choose the best. All solutions are the best. And according to the study which we did in these papers, we are going to play a little bit with this multiple solution. So 20 years ago, when we sum up all this solution, we just average them. So we have n kind of solution, and each solution has 1/n probability. So all solutions are good. So let us do the simplest procedure, just the average. But because every solution is good, let's play with the linear combinations of the solution. So what we need, the only thing, if we have some normalization of the f at x, then the sum of this ci should be 1. In principle, it must not be all positively definite. Some of them can be negatively definite, but the only thing, it should be 1. So what happened in this case? In this case, we can play the game. So for example, I just give the cartoon, and this curve is the average of the solution. Say it's around 1,000 solution, which is obtained in several hours. And we have the answer, which is the average when average C from J is 1/n. So let's introduce the following thing. We add some function, the game with them. We add some functional to our, have to say, to this measure. And try to do the following. We set the functional which force our solution go through this point. You see it's point outside of the averaging, and minimizing this measure, we get another solution. And we ask ourselves the questions: is the solution good? And the answer is yes, because if the deviation measure m, which is the Euclidean measure, does not change more than few %, and still there is no extra features, this answer, which is red, is as good as this answer, which is yellow, because both of them is a linear combination of the good solution. And this linear combination has absolutely, almost absolutely the same measure of deviation, yellow one and the red one. So this means that both of these solutions are good. So we can play further. Can we pull it a bit more? And we try to pull, and for example, in this case, we have the following situation. And in this situation, we say, is this solution is still good? And the answer, it's not good. So it means that this kind of linear combination, which passes through this point, is not good because it does not satisfy them anything. First, we see the extra structures which appeared. Second, usually the deviation measure in this case, when you see the extra structure, it's very sharply goes up, so it's twice as the deviation measure of the initial yellow curve. And sometimes, which is known here, we have the negative values for the positive definite spectra. So which means that it's okay for us if we pull it to this point. So it means that yellow solution and red solution are both good. And this is give us the possibility to understand what kind of the reliability of the data we have. So because all these solutions and their sum satisfies the error bar of the input data, both solutions are good, but this solution is not good anymore. And this is kind of the thing which how we can play with the sum of different solutions and can get this answer. So to study this, we played several years ago for the blind test. So one of the guys in Massachusetts prepared the test for us, and we were sitting that time in Munich. In Munich, we tried to reproduce solution without knowledge of the answer. So we just know the function g from n, and we don't know the a from z, which was sent to us from Massachusetts. And we try to understand what's kind of the reliability of the data we have. So for example, the spectrum which we use, this is low energy peak, which is usually well reproduced by analytical continuation with such kind of kernel. And this is the high energy peak, which is usually somehow possess the difficulty for the analytic continuation. So if we have the noise level 10 to the minus 3, it's the relative error bars, then the low energy peak is well reproduced. By high energy peak, it's almost, have to say, it's difficult to predict. It's good to predict its position, but as for width, this kind of blue solution is as good as this solution, which is shown here by the dashed line. It's 10 to the minus 3. If it is 10 to the minus 5, and 10 to the minus 5 is already, how to say, it's a dream of Monte Carlo people. When they have 10 to the minus 5, they think that they can do everything. And in this case, the low energy peak, you see that we can reproduce it precisely, absolutely precisely. And the low energy peak still has such kind of uncertainty that this blue peak and this peak, which is by dashed line, is really reliable. So it's within the error bars of the input data. And the only thing which show how much sometimes it is useful to have some knowledge of the data. For example, if the low energy peak is not a peak by a delta function, for example, we know that this state in the bottom of the spectrum has no decay. It's kind of the stable quasi-particle. In this case, the low energy peak is a delta function. And if the low energy peak is a delta function, there is a big reliability for the high energy peak. If the precision 10 to the minus 5, which is the proud of the Monte Carlo people. And when the low energy peak is a delta function, then high energy peak, we can prove that this is absolutely reliable peak, even the width. So because my time is up, I come to conclusion. So I just wanted to show you that there is a stochastic approach. And this stochastic approach has no corruption of data by the regularization because we avoid it. Second, it can list most of possible solutions which are dictated solely by the data, by the input data. There is no regularization. And our philosophy is not search for one which is best or quasi-best solution, but we can list all possible best solutions, every of which is the best. And finally, you can ask why it was not invented before. So this method, which is ideologically is simple up to idioticity. So because in a previous time, it was not possible to obtain 1,000 of independent solutions during one night and to play with them. And that is all I just wanted to say, that using this method and diagrammatic Monte Carlo, we were able to make some different things in the condensed matter theory. I just restricted publication to one journal. To figure of letters, there are many other things. And then I came back to my conclusion. And thank you for your attention. And here's my conclusion on the screen. Thank you very much.
Thank you very much, Andrei, for this very interesting, clear-cut, opinionated presentation. Very much appreciated. Do we have any questions at this point? I have one myself. Let's see. Do we have? Maybe I'll just start. So I very much like your philosophy behind your work of saying we should essentially be sampling this problem, and we should be thinking of sampling. I'm coming from a Bayesian point of view. So for me, when you say you're averaging over these solutions, to me this is Monte Carlo sampling of a posterior. So I very much agree with you that there is not the best solution. There are many solutions compatible with your data, and they should be sampled over. What I, however, am a bit disagreeing with you is the statement that there is no regularization in your approach, because you restricted your boxes that you use to sampling to positive definite boxes, if I understand. And indeed, if even though the likelihood by itself has these many local extrema, if I restrict to only positive definite functions, indeed, this reduces massively the different local extrema in the likelihood. And then I can see that such kind of a sampling approach actually does work. So don't you see that, or wouldn't you acknowledge that positivity is a form of regularization in your approach?
In our case, I agree with you. It's a good thing which you tell. So because in our case, all the spectral function and correlation function are just positive and definite by definition. So in our case, it's not restriction. But if you have real negativity, of course, you need to restrict your solution for some upper level and lower level, and this is kind of regularization. But still, within the same level of restriction, you can exercise the same philosophy from the item 1 to the item 4.
Yes.
So just say, okay, my solution is no larger than 100 and not smaller than minus 100, and then you go the same way. And
Very
this
good.
is, of course, is restriction. It's called the constraint.
Exactly.
Yeah.
Very good. Very good.
It's not the regularization, it's constraint.
Okay. Very good. Thank you. Harvey, you had a question?
Yeah. I was wondering how these solutions are sampled. So are they sampled by starting with different initial guesses? Or, how do you generate an ensemble of solutions? Because this distribution in the end matters, right, for your average.
So it's enough for us to do the following things. So every time which we want to get the solution, we choose the initial solution by the random number generators. A number of rectangles is positioned with heights and then normalize it to some norm. And then every time we do absolutely the same procedure, but start from stochastically generated initial configuration. And every time we get an answer, and it doesn't matter which method you use to minimize. It can be some regular method, it can be some quasi-stochastic method. In the end, you have different answer, and every answer is statistically independent.
Okay.
There are some approaches. It's Galli from Italy, which use a different approach. For example, instead of generating some different initial configuration, they just take the data, divide input data, divide it into different batches, and use different batches as a contribution for the generating of the different stochastic solutions. So it doesn't matter which way you use to get the statistical solution. So first is what we use, and we were the first to use it. It's just a different initial configuration. So then was approach of Galli, where they suggested to generate it the same initial solution, but takes a different batch of the data from the input data. And there is the approach of Padé approximation from the Sweden group from Uppsala of Ole Eriksson, and they used the Padé approximation, but they played with a different choice of the poles. So in every case, if you exercise the stochastic, you need a lot of different independent solutions. And in every case, you choose your own strategy to find it.
I see. Yeah. So I suppose depending on this method you use to generate an ensemble of solutions, I mean, you have a slightly different distribution, right, of these solutions. So that must have some impact on the
I guess if you do an accept reject, you really sample the likelihood, essentially. So
no, I mean, implicitly there's some input default distribution in these solutions that you generate, right?
You are completely right, but within our new philosophy, it is not a tragedy. So you tell that within the different approaches to generate the stochastically independent solutions, we have different sets of this Ri, which is every particular solution of our fit. But then our answer is we are not going to stay with this Ri. We will play with the coefficient of the linear combination. And we try to look at every possibility which still satisfies the data. And within this thing, if we have a representative set of solutions, which is when we get thousands or 10,000, and regardless of the different constraints, it usually gives the same average. So whatever you do.
I will go in at this point and go over to Hiroshi, who has a question, and we are transitioning therefore also to our next speaker. Did you have a question particular for Andre?
Yeah, but maybe we can discuss.
Maybe we can discuss it in the discussion. Very good. Because
okay, thank you very much for attention.
Exactly.
I'm stop sharing.
Perfect. And we thank you again, Andre. And we are now coming to our second speaker, Hiroshi Shinaoka from Saitama University. Also, he is a member of the condensed matter community, and I'm very happy that he agreed to present at our workshop. And he's telling us about a sparse modeling approach to analytic continuation of imaginary time data and in quantum many-body calculations. Hiroshi, please take it away.
Thank you. Do you hear me?
Yes.
Okay, thank you for the invitation. I'm quite happy to be to join this night workshop, and many people from different fields and on the same topic. Okay, so I'm Hiroshi, and I'm from Saitama University, and let me check my, I'm going to talk about some series of work based on collaboration, international collaboration around the world, right? So Saitama University is a small national university, but well, it's quite close to Tokyo and just 1 hour by train. From Tokyo Station, of course, Tsukuba is quite close, and Riken is probably just less than 30 minutes by car, but it takes more than 1 hour by train. So we don't have good connection. So my expertise is actually developing first principle ab initio method for correlated materials like cuprates and other fascinating materials. And especially I'm interested in continuous time quantum Monte Carlo and dynamical Mayfield theory. And I did postdoc for 3 years in Switzerland in Matthias Dorius and Philip Werner's group. And I enjoy quite a lot Swiss life and biking. I'm doing a professor now in Saitama University. This is small, but Professor Kajita used to be an undergraduate student before he moved to University of Tokyo. Anyway, so I'm going to talk about two things, essentially. One, the first part is stable analytic continuation based on two ingredients, so-called or intermediate representation compact basis, special basis for imaginary time correlation function, and signal processing technique sparse modeling. And in the second part, I want to focus on the basis itself, and I will show you this is quite useful when you handle numerical data in imaginary time. Okay, so let's get started. So maybe I can skip this slide because everyone in the workshop knows why analytic continuation is very difficult. But I take one sample from my field. We sometimes do continuous time quantum Monte Carlo on imaginary time, and we get some very accurate imaginary data with very small noise. But if we continue this to real frequency using like per day approximation and in a naive way, so we still have a good result at low frequency, but result is pretty bad at high frequencies, and essentially we get random data. So we have to stabilize it, and if possible, we want to get more precise result. And there are many sophisticated methods like machine learning things and stochastic method and many other things. But what I want to answer in this talk is what information remains in your imagined time data and how we can extract the relevant information from your noisy data and how to reconstruct approximate solution in a stable fashion. Okay. So the first part of my talk is based on this paper. And Otsu-san is now professor in Okayama University, and Ozeki-san is a data science guy. He used to work on spin glass, but he decided to change his job to data science because it's more like easy to find job and money. And he's now doing well. Yeah, quantum computing. And Yoshimi-san is a software guy. And so now let me give you some example how sparse modeling works in signal processing. This is a picture from this reference. And this is very clean without, small noise, with small noise. And we can add some artificial noise on the top of it. Just Gaussian noise. It's an experiment. And if we do sparse modeling and some special techniques, regularization, we somehow denoise the picture. Of course, we can't get the exact result. It's impossible, but we still reduce the noise level to some extent. Okay, there's another example. And this is by Ozeki-san. And this is an MRI brain image from MRI. And the right one is result from observation from full-time measurement. And here we have result from, we reduce measurement time by a factor of 4. So all details are smelled out. And when we apply sparse modeling, we recover some of them, some of features. And of course, this is not 100% accurate, but still we see more details. So, and there are two ingredients in sparse modeling, roughly speaking, of course. And one is a basis where your signal, your exact signal is compactly represented, which means you need only a few non-zero coefficients to represent your signal. So you need such a sparse basis. And then you apply some regularization and to separate your relevant coefficient or information from noise and noisy data. So let me illustrate how we can use these techniques for analytic continuation. Yeah, this is an equation which has appeared many times in this workshop. And this is spec function, and this is a Green's function in imaginary time tau. And those two objects are connected by the kernel. And this is the integral equation. And this kernel is either fermion or boson. And so we are discretize this integral equation in some sense. For example, use a uniform mesh in tau and omega. So you get you obtain our matrix form, right? G is now a vector, and K is a matrix, Rho is a vector. And when we apply singular value decomposition to this kernel K, so you get our singular matrices, I mean, a unitary matrix consisting of singular vectors, and you get one more unitary matrix, and S is a diagonal matrix consisting of singular values, positive, non-negative, and decreasing super exponential due to the nature of this kernel. And when we transform or project this G and Rho on those bases or unitary matrices, you get some relation between expansion coefficient of rho and g in those bases, SVD basis sets. So this relation tells you that numerical analytic continuation is not possible in naive way because this rho L depends on the system, right? Your true spectral function. But this is multiplied by SL. And even if you have a small noise, yeah, let me, okay, something wrong. Yeah, this is the illustration. If you have some spectral function and you go through this kernel and you get some emergent time data right, and expansion coefficient at large L, rho L, so it becomes very small, exponentially small. And once you have some noise in G of tau, and those small coefficients are really affected by this random noise. And that will be amplified by this small single values. So you get almost random data. So that's why we need regularization probably. So yeah, so exact numerical analytic continuation is not possible without any prior knowledge. That's my opinion. So let me show you another example. And this is a model spectral function consisting of 3 peaks, and you transform to G of tau, and this transformation is safe, and you add some artificial noise, and the blue crosses exact data, and this is with noise. So you can see that the noise level is somewhere here, and only 7 components remain above the noise level. So you have only 7 degrees of freedom in your numerical data. So the question is how we can reconstruct the spectral function from this data without prior knowledge. Of course, we can't get right exact data, but still we should be able to reconstruct some approximate solution from this data. So this is our strategies. This is based on a so-called Russell equation, and this is a data fitting part. This is chi-squared, and we add some other regularization term based on L1 norm. I'll explain how it works in the next slide. But essentially, this induces our sparse solution where some coefficient rho L are completely 0 and only relevant parameters remain finite. And what I have to emphasize here is that we can minimize this Russell equation with some positiveness and some rule constraint and fast and stable and convex optimization problem. And no default model like Maxent, apparent no default model because still choose some measure, but and lambda hyperparameter lambda control balances between fitting and sparseness of your solution. So you have to optimize it or choose appropriate value data. Okay, let's give me some example how to show how this L1 regularization induce a sparse solution. And this is a right ill condition inverse problem. Y is the data to be fitted, and X is your parameters in fitting, and A is a coefficient matrix. If A is right, if the dimension of Y is smaller than that of X, so you have more fitting parameters than your numerical data. So this problem is ill conditioned. So you can't get a unique solution. And for this simple example, so you can immediately see all points on this line are solution to your inverse problem. So there is no unique way to take out one of them from those degenerate solution. So that's why we usually need a regularization. And different regularizations lead to different approximate methods of analytic continuation in our case. So our famous one is L2 regularization, sometimes called rich regularization. And so that means, so let us choose the solution that minimize L1 norm out of the degenerate solutions. And this circle is a contour of this L2 norm. And you can immediately see that the solution is the cross point of this line, this circle here, where x, both of x and x2 are finite. And but in contrast, L1 regularization, so the contour of L1 norm, this is just sum of absolute values in your parameters. This is somehow has edges. So this is a completely different from a circle. And this square touches this line here. If we increase the size of our square. And here, so x1 is 0, non-zero, but x1 is completely 0. So we can extend this idea to a higher dimension, and we can do some math. And in general, L1 regularization suppresses irrelevant parameters to exactly 0. So that's how Russell equation works. So let me use these techniques for analytic continuation. So as usual, the hyperparameter must be chosen. And one easy or naive way is monitoring chi-squared by changing lambda. And at some point, here we have nice fitting. Increasing lambda, you increase the sparseness, and at some point, chi-squared starts to increase, and you enter an underfitting regime. So maybe optimal value is somewhere here. And a more accurate or more sophisticated method probably monitoring cross-validation. But still, we usually get similar result. And when we apply this minimize this cost function for optimal variable lambda, so we get this result. So the red circle are obtained by SPM, sparse modeling, and all the other parameters, well, suppressed to 0. So they SPM says only 7 components are relevant in this fitting. And when we reconstruct the signal, our spectral function, we have nice agreement at low frequencies. Of course, we have some deviation at a high frequency, but still this fitting is quite fast and as fast as Mach-Cent and stable and convex. And we can actually extend this idea to covariance metrics and also matrix varied correlation functions. And there is some, So, and we have our open source implementation of this algorithm and on GitHub, and we have nice tutorial and sample result. And we are going to release version 2 quite soon with improved stability for bosons and improved determination of hyperparameters based on cross-validation score. And this is quite new, so there's no single best analytic continuation method. Probably we should compare a result with different methods, and we have to find bad case and good cases. So I'm happy to get any feedbacks from you. Now, I will spend a few minutes on this part. And this is based on a recent review article from Emmanuel. He was in the discussion last night. He also joined. So we saw that actually we have 3,000 points in our G of tau, but we have only 7 points in the SPD basis. So what's the difference? So actually this SPD basis should be a good basis or minimal basis for imaginary time correlation function. That's our idea. So I want to show you that how the SPD basis look like and how we can use this compactness in many body calculations in imaginary time formalism. So again, this is a spectral function, but the difference is we have a now frequency cutoff omega max. So essentially this equation has two parameters, inverse temperature beta and frequency cutoff. And actually only the dimensionless parameter is lambda beta times omega max. So we do a singular expansion and we get singular values and two basis functions for tau and omega respectively. So we call them R basis because those basis functions somehow are connecting frequency, imaginary time and real frequency things, domains. So singular values decay super exponentially and even at large lambda beta, and the number of singular values above some cutoff value grows only logarithmically with increasing beta. And those are our basis functions for tau and omega for the first few basis function. The first one is just a curve, right, in tau. And as for larger L, we see more roots around tau equals 0 and beta, where we usually see some futures in imaginary time numerical data. And the number of roots is exactly L. So it's something like Rujando or Chebyshev polynomial, but it's not polynomials. And for real frequency, we have roots around omega equals 0, and it's become denser with increasing L. And we only see some futures are at high frequencies when we increase L. So low L basis functions do not have any futures at high frequency. That's why analytic continuation at high frequency is completely difficult, because to reconstruct data at futures at high frequency, you have to reconstruct low L at large L, and that is really easily affected by numerical noise. So now let's look closer at our basis function. And interestingly, the R basis function converges to Jandot polynomials in this high temperature limit. But at finite lambda, those basis functions are not polynomial and there's no analytic norm form. So you have to generate numerically. But it's quite interesting because Rujando basis polynomial has been known for centuries, and we have now some physical extension to imaginary correlation function. And we can now we have to model spectral functions, semicircular poles, and expansion coefficient of spectral function are actually for delta function at high frequency, it doesn't decay. But this multiplied by our singular values. So if you are interested in only imaginary time data, this decays super fast. And this is guaranteed by singular values. And if you want to store your Green's function data of this model with 8-digit significant digit, so we need only up to 100 or 200 basis functions. And in contrast, if you do conventional methods, Matsubara, Rujando, you need, a lot of basis functions or coefficient. So, And this basis function can be generated by a Python and C++ library, and pre-computed up to 10 to 7 lambda. It's quite low temperature, and it should be enough for any practical calculations. Okay, the last slide. And we have been working, now we are trying to use this, of course, we found this basis when we do sparse modeling, was doing sparse modeling, but we found this quite useful in many situations. You can use it as a denoiser, or we can solve diagrammatic equation for materials directly in this basis. And we can do real material calculations very efficiently. And we can extend this RR basis to two particle quantities, like two particle Green's function or vortex functions in condensed matter physics, and we can solve beta equation quite efficiently. And now I think this is going to be our standard tool in our field, I hope. Okay, this is my summary, and this is my first talk in the front of lattice QCD people. So I'm happy to any collaboration. And if you have a question, just send me an email. I'm happy. Thank you.
Thank you very much, Hiroshi, for this very interesting presentation. It was very insightful. Do we have any questions at this point? So maybe as people are gathering their thoughts, I had just one comment maybe. When you introduced this L1 norm that supplements the likelihood minimization, again, coming from a Bayesian perspective, I want to interpret this as some sort of a prior probability distribution. And one thing that for example, the Tikhonov method often is mentioned as saying it doesn't have any free parameters. And my comment here would be, in some sense, for example, when one writes the norm of rho, one could, for me, coming from the Bayesian side, this to me says I actually have written there rho minus default model norm, and I've decided that my choice of the default model is actually the value 0. So what you're what one says, and that is, it's a valid strategy, that okay, we want to and that was your statement, I think, you want to minimize the irrelevant parameters. So set the these parameters to 0. And I would just like to comment that this is a choice of the construction of this method, isn't it?
Yes, exactly.
You could have said, okay, maybe there could be some physical reason why some of these parameters should have a certain value. Then you could amend this procedure by saying, okay, I would like the L1 norm to drive the rho to a certain value.
Yeah, actually, I'm not sure if I understand your comment, but well, actually, we are trying, we bias the solution, of course, because we somehow prefer a solution with a smallest number of non-zero elements coefficients. So I think this, well, I said there's no apparent default model here, right? But this is not true. We somehow introduce some bias or default model.
Okay. So this wasn't meant as a criticism. I just wanted to see that there is actually the freedom to say, I would like to, because of physical constraints, for example, that you can amend this by saying, I would like to drive my parameters via the L1 norm to a certain value and not just to 0.
Yeah, but this value is not known, right? Usually.
That's so on the lattice QCD side, for example, we sometimes have the the situation that, for example, through perturbation theory, the behavior of the spectral function at very large frequencies is known, and then one might want to somehow match the solution to these kind of
This can be done. Actually, we introduced some rule, and we can extend it to higher moments, so we can minimize this cost function in subspace with the exact higher order moments.
Very good, thank you. This is interesting. Javi, please.
Hi, I was just wondering, you showed the difference between using the L squared norm and the L1 norm. Yes, you illustrated this on the slide.
Yeah.
I mean, in practice, what are your observations? I mean, do you see some definite advantage of this L1 regularization over the L2 one?
In analytic continuation?
Yeah.
Yeah, we haven't done a lot of examples, but yeah, L1 is more stable. I mean, in the term of oscillation, random oscillation, because this Q is completely irrelevant parameters.
So it's a stronger regularization in some sense?
I think so. Yeah, I think so. In terms of truncation of expansion coefficient.
Okay.
But we haven't invested the L2 extensively, so maybe we should take at some point more carefully.
So did I understand it correctly that you, in this method, you first go to this SVD basis?
Yes.
And in addition, you have that L1 regularization term.
Yes.
There are both things in there.
Yeah.
Is that right? Yeah.
Yes.
Okay, thanks.
And with some additional physical constraint, like some rule.
Some rule, yeah.
So
I mean, this is like additional data, an additional data point also, which is exact. Or
oh yeah, maybe there's some good solver for this kind of equation, Russell equation, and we can explicitly introduce these some rules into the optimization. So this Russell equation is widely used in signal processing. So people invented a lot of nice solvers.
Okay, thank you. Thank you.
Very good. I do not see any further questions at this point. Let's thank Hiroshi again for this very clear and insightful presentation. And we are coming to the virtual coffee break of the workshop. And we'll reconvene at the full hour with our next speaker, Etsuko Ito. And the next session will be then chaired by my colleague, Anthony Francis.